Roger Penrose, welcome back to How the Light Gets In.
My pleasure.
Well, you've been a friend of the II and How the Light Gets In since its early days, so it's a great pleasure to have you back. A Nobel-prize winner now, so many congratulations on that important recognition from us. You spend much of your career tackling questions that touch on the foundations of physics and the philosophical questions that arise from some of them. How have the attitudes changed within the academic scientific community towards people like you who aren't afraid to engage with both physics as well as the philosophical questions that arise from them?
I think it's got more acceptable in a way. I'm not quite sure. I think there's one of the big issues, I think, was consciousness, because it's become more acceptable as being a scientific topic. Whereas I think, you see, I wrote the book, The Emperor's New Mind, rather not realizing that I wasn't supposed to write books like that. That consciousness was something, wasn't a scientific topic, I think. And that's become more allowed, I guess, in a sense.
Would you say that beyond consciousness, that the deeper questions in physics end up touching on these bigger questions that sometimes belong to philosophy? How do you understand the relationship between philosophy and physics when it comes to these foundational questions?
But I think a lot of these things, I mean, I'm sure the connection between philosophy and physics is quite old, and probably even before people knew much about physics, it was philosophy. So I'm not sure I would say that's so new. I was only saying I think the consciousness thing has become part of science. I don't think I can see that there's more of a connection between physics and philosophy. I mean, there are some people who still would take the view that if you're just waffling about philosophy, then, well, I mean, there is the question of the collapse of the wave function, which I think maybe a lot of people thought was philosophy. I don't know. I take the view that it's genuine physics which you don't yet understand. Not that we just don't understand. Not understanding rather implies that the theory is out there which we haven't grasped. And I think often people take quantum mechanics in that sense. They say it's a mysterious subject, and you're not going to be able to understand it properly without really realizing there's that deep mystery in it. That's not the way I like to look at it. I tend to look at the problems in quantum mechanics are really that we don't fully have the theory, that the collapse of the wave function is a physical process which needs to be understood properly, and there are experiments which probe the nature of that area. So I'm trying to bring that thing more into the realm of physics rather than as it might have been sort of hovering around as a philosophical issue.
So let's talk about this topic of consciousness. As you mentioned, traditionally it was thought to be a purely philosophical topic rather than a scientific one. But from the early days of quantum mechanics, there was this interpretation that consciousness had something to do with the collapse of the wave function, that somehow consciousness measurement involving a conscious observer was the thing that made the wave function collapse from a state of superposition.
Yes.
But you're not very convinced by that interpretation.
Well, you see, I have almost the opposite view. I think the terminology drove people in that way. It's like saying you make an observation. And when you made an observation, you had to change the rules. Up to that point, you take the Schrödinger equation as describing the evolution of the physical world, and then when an observation is made, it's only telling you the result of an observation. But then the observation was really something outside physics. Whereas the view I would take is that we should be looking for a physical theory which reduces the state. We don't have the physical theory yet, although I think, in my view, it's going to be something to do with how gravity relates to quantum mechanics. And that when a system becomes big enough for its gravitational fields to become significant, then you have to bring it into account. And the measurement process, it's not really a measurement process, it's a collapse of the wave function process, which is actually something which happens. It's independent of how you only measure something because you tie the system you're observing into a bigger system, which is making the measurement. And so you're really looking at how that physical system behaves as a whole.
As you said, your view on the relationship between quantum mechanics and consciousness is almost the opposite of this interpretation of the measurement problem. Can you tell us a little bit about your view? In your view, consciousness in the brain arises out of the collapse of the wave function. Can you explain that puzzling claim? What does that mean exactly?
Well, there's sort of reasoning behind why I think that view, if you like, or I can say more about what the view is. I mean, the reasoning behind it had to do with the issue of, it really came from my attendance of a course of lectures given by a man called Steen in Cambridge, when I was a graduate student in Cambridge, and I went to 3 courses of lectures which were nothing to do with the topic I was supposed to be doing, which was algebraic geometry. And I went to a course by Bondi on general relativity, which was certainly very relevant to what I did later. Lectures by Dirac on quantum mechanics, where I did the puzzle of the collapse of the wave function became more evident to me. And a course on mathematical logic by a man called Steen. And his lectures made clear to me, at least what seemed to be clear to me, that conscious understanding could not be an algorithmic process. There's something different from computational processes going on. So if we believe that whatever we are, we're sort of physical structures, then do we act according to computational laws, or is there something in the laws of physics which is outside that? And the view I maintained at that time, because of the lectures, Steen's lectures on mathematical logic and Gödel's theorem, it seemed clear to me that conscious understanding had to be something which was not computational. And then the question is, if it is a physical process of some sort, what could that physics be? And if I think about classical Newtonian mechanics, there didn't seem to be much chance. Even general relativity, because you could put these things on computers. There is a bit of an issue about the fact that theories depend on continuous parameters, whereas computation, as normally understood, is a discrete process. And the way we do calculations in physics to mirror what's going on in the world, and put them on computers, we regard these as approximations which you could refine as much as you like. And they're still then computational processes. There's a little bit of a problem there about whether there might be a distinct difference in continuous evolution from discrete processes. But I didn't think that was the answer. It seemed to me that there had to be physical processes which were not computational. And the view is that this is conscious understanding has to be one of these. And where in physics do we see anything not computational, or anything of relevance that would be not computational? And it seemed to me it had to be the collapse of the wave function.
Why is the physics of quantum mechanics and the collapse of the wave function specifically non-computational compared to the rest of the physics?
Well, the argument's really the other way around. It's not saying why that's non-computational. It's the argument was, if we need something non-computational, what could it be? The argument's that way around. And if it's just classical processes, even general relativity, even if it's quantum with regard to following the Schrödinger equation, I see nothing non-computational in that, because these things you could put on a computer. So if there is something non-computational, it's got to be outside any of those views. And what has a chance of being outside? Well, collapse of the wave function. So it's more a process of seeing, process of elimination rather than expecting to see it there.
So that was your reasoning for thinking there was a connection between consciousness and the collapse of the wave function.
Yes.
Now to the understanding of how to think of that. How do you think of this phenomenon? How do you see consciousness arising?
The collapse of the wave function, how do I see it? Well, I think that required a lot of refinement as time went on. And in fact, when I wrote The Emperor's New Mind, although I had the view, that general view, I didn't have what I now believe to be the right criterion. Although I did think it was gravitational. What I regard as being the right criterion, or at least towards being the right criterion, is dependent on an argument which I can't remember exactly when I first thought of this argument, but it's showing an incompatibility between the principle of equivalence, the equivalence between a uniform gravitational field and an acceleration. So it's the Galileo principle, if you like. Imagine a big rock and a little rock dropped from the Leaning Tower of Pisa, and they drop together, as Galileo was clearly pointing out. And that principle is the basis of general relativity, combined with special relativity, if you like. You've got speed of light being fitted in with being a constant of nature, and time and space being part of one structure of space-time. And then Einstein modifies that picture by introducing the principle of equivalence and saying that gravity is not a force. It's you can get rid of it by falling freely with it. However, if the force is not uniform, or the gravitational acceleration field is not uniform, you're led into a curved space-time. Now, the argument that I was making was that if you have a principle of equivalence, there are two ways of looking at a quantum system in which you want to take the Earth's gravitational field into consideration. The way that any sensible physicist would use, and when I say sensible, I mean just the normal way, would be to do what's called putting a term in the Hamiltonian. You have your standard quantum mechanical procedure, and you accommodate the Earth's gravitational field by putting this extra term in the Hamiltonian. That's the Newtonian way of doing it, if you like. You're thinking of gravitational force, it's just another force. Then you say, what's the Einsteinian way of looking at it? Well, you say, take the principle of equivalence seriously, and falling free, if you have a uniform gravitational field, you can consider describing that system with a coordinate system which is dropping freely. And then there is no gravitational field. It's just using an accelerating frame. And then you compare the two procedures, and what you find is that they're almost exactly the same, but the key is in the almost. The difference is in what's called a phase factor. And the usual attitude in quantum mechanics is to ignore the phase factor. You say these two states are the same. So you could ignore it. That's not quite fair, because you look carefully at the nature of this phase factor, and you see it involves a term where the time comes in cubed. The gist of all this is that you are doing a different quantum field theory. You have to know what the quantum vacuum is in order to do your quantum field theory properly. And the vacuum is different if you take the Newtonian perspective and the Einsteinian perspective. Again, you might say, who cares? Stick to your vacuum and you get a consistent answer. So why bother? This is all right as long as your field is a constant field, like the Earth's gravitational field. It's a bit like going back to Galileo and say, you can get rid of gravity if you fall freely in it. But it doesn't quite work if, as you move around, the field is in a different direction. So it's all right to say you can get rid of this field vertically downwards here, but what about in Tasmania or something? You see, it's a different direction. So to hang together your theory where these directions are moving as you move around is a challenge. And what it leads you to is an inconsistency. You can't really quite do it. And so what you have to do is try and estimate the error involved in this. And that estimate gives you have to do a little bit of mathematics. And you see that that comes to a sort of uncertainty in the energy of the system. And that uncertainty in the energy in the system you can interpret as a lifetime of the system. This is going to Heisenberg, and you have this Heisenberg time energy uncertainty. So if you have an energy uncertainty that is related to a lifetime, you get this for particle physics. For an unstable nucleus, there is an energy uncertainty which is inversely related to its lifetime. So the argument then is your quantum superposition, which has this tension in it, which is an energy uncertainty. You can work out the lifetime. So that lifetime tells you how long a quantum superposition will last. It turns out that this actual formula I had was found already by Dioschi, another physicist who some years before me had put that forward. So it's sometimes called the Dioschi-Penrose model. The rest of the theory is not quite the same. He has a different way of looking at things from me. So they are different theories, really. But the lifetime is the same criterion as he had. Now, when I wrote The Emperor's New Mind, I didn't have that quite right. And when I say quite right, I didn't have the current view I have on this. Whereas in Shadows of the Mind, which is the next book I wrote, I put in what I now believe to be the correct criterion. There are some subtleties about it which I hadn't realized at that time. And these lead us into interesting territory.
So some of the work you did on this was with a neuroscientist, a colleague of yours, Stuart Hameroff, who wrote to you, having read your book.
Yes.
And said that there are structures in the brain that would allow for the phenomenon that you were describing in that book.
Yes.
I guess my question is does this emergence of consciousness only happen in the brain? And do we need the structures that we find in the brain for that to happen? Or is it a phenomenon that we're going to observe in other parts of nature?
OR stands for objective reduction. That means the reduction of the quantum state as an objective process. But it's an acronym which is deliberate, namely it spells OR. So it means rather than having this and this simultaneously occurring, one or the other happens. So it means OR. And the ORC part means orchestrated. That's the vaguest part. We don't really know what orchestrated means. But somehow the collapse of the wave function has to be under control in a way. And that's presumably how the brain sorts it all out. I mean, there's a lot of unknown about it. And the scheme has certainly evolved very considerably since the original ideas. Microtubules were a revelation to me because I didn't know anything about them. And I learned a bit about nerve propagation and realized it was way off the mark if you wanted to have something which could preserve coherence at the level you would need here. And the way that I understood nerve propagation operated, it would disturb the environment in a completely uncontrollable way, no way of preserving the coherence. So when Stuart wrote to me and informed me about microtubules, I thought that sounded much more promising. You could imagine at least that there was a preservation of coherence at a level that may be okay. There's a lot more to the story, and certainly the story has evolved very considerably, largely, I think, on the neurobiological side. Stuart has much more firm ideas about where this happens. For example, there's a big problem, which always struck me as a big problem, even when I was writing The Emperor's New Mind. I mean, you've got this part at the top, this cerebrum, and then this part back underneath called the cerebellum. And even at that time, I didn't realize, I didn't know, I don't think the scientific community knew, that the cerebellum has more neurons in it than the cerebrum. If you're just looking at a complicated network of something or other, why is the cerebellum completely unconscious? Whereas it's got more cells in it, and they're all wired up, also in a more, what you might call, sensible way. That is to say, controlling the right arm is not done on the left, as the cerebrum does. You have this crazy-looking organization, obviously done for some deep reason that we don't fully understand, because the cerebrum doesn't worry about that. Cerebellum doesn't worry about it. The left hand controls the left hand, and the right hand controls the left hand. It does what you might think you were designing a computer to operate things. Whereas, what's the difference? Well, a difference, which is what Stuart is concentrating on, is these things called pyramidal cells. They're a particular type of cell which is not found in the cerebellum. And Stuart thinks that's where consciousness is really operating. And he's worked these things out much more detail now than we had in those days.
I wonder what you make of quantum computing now that it's becoming a reality. It was in the past the speculation of whether we could build quantum computers. Now it seems that we can. Does that affect the way that we might think of consciousness arising in non-human entities?
Not really. You see, the term quantum computers has changed rather since when I first heard about them. But basically, there is no attempt to do something which isn't a computation in the ordinary sense of the word. You may want to speed things up, do them faster. You have some class of problem which you can speed up using these quantum computer devices. But they're not using the collapse of the wave function. A quantum computer, as that term is used now, is still an algorithmic device. Now, this means that we need to go beyond what's called a quantum computer if we are going to harness the reduction of the state as something which is useful to us. That's way off what we know how to do now.
Another philosophical question that sort of arises from physics is, can something come from nothing? And for many years, the standard cosmological model was answering that question affirmatively. The Big Bang was supposed to be that. It was a creation out of nothingness. But you have changed your mind on this, and you seem to be returning back to the idea of this steady state, eternal universe. Can you tell us about what do you think now and what made you change your mind?
Yes. I don't think it is true that when I first seriously got interested in cosmology, it was through the steady state model. And it came about for perfectly good reasons, because the age of the universe seemed to be less than the age of globular clusters, and that needed an explanation. Well, the steady-state model was one route to go. It turned out there was a mistake in people confusing Cepheid variable stars with the wrong ones. But the idea of a steady-state model rather appealed to me, I think. When the microwave background was discovered and it seemed that the Big Bang really was there, Dennis Sharma, who was my mentor very much, changed. I had a lot of respect for him. He changed his mind, and he went around lecturing to say I was wrong previously. And so I went along with that too. But nevertheless, the background of the steady-state model, I think, was something that appealed to me. It wasn't the reason for introducing CCC. The reason for introducing, that's conformal cyclic cosmology, reason for introducing that idea came about from what regarded me as a huge paradox. You see, I had my singularity theorem, which eventually won the Nobel-prize, and Stephen Hawking picked up on this and used the same sorts of arguments and developed them and improved upon the arguments and developed them so as that you could apply them to the Big Bang. But it was all saying, so, well, this is part of one story. And the argument was normally made that the answer to that story is quantum gravity. You have to combine gravitation with quantum mechanics. But that never seemed to make sense. Well, I say never seemed to make sense. It seemed to me that it had to be a very peculiar theory, which wasn't an ordinary quantum mechanics, which had to be asymmetrical in time, because the singularities in the future in black holes are completely different in structure from the one that we know directly, namely the Big Bang. And this has to do with the gravitational degrees of freedom being completely cancelled out, completely reduced to zero in the Big Bang. And first of all, I just sort of postulated that's it. But then one of my graduate students, I can't remember whether he was still a graduate student at the time, this was Paul Todd. And Paul Todd had a different way of saying how you characterize the initial state. You just don't say, well, the gravitational degrees of freedom are zero. You say that the Big Bang can be stretched out to be something nice and smooth. And that was a better way of talking about it. But it led me to think, well, you stretch out the Big Bang to make it nice and smooth. You can squash down infinity to make it nice and smooth. And when you think about it, they seem very different. The Big Bang is hugely dense, hugely hot. The remote future is hugely rarefied, hugely cold. It's about as opposite as you might think. But if you squash it down by this conformal squashing, temperature goes up, density goes up. Stretch out the Big Bang, temperature goes down, density goes down. They seem rather similar. So I postulated the idea that the Big Bang is the continuation of the remote future of a previous eon, as I called them. And that makes sense of lots of things that are puzzling in the Big Bang. The uniformity is necessary because of the uniformity of the remote future. There's a thing called inflation, which is part of current cosmology, which always worried me. It seemed a very, very artificial idea. You need an exponential expansion hiding in the Big Bang, which seemed to be artificially put there. But if you've already got an exponential expansion, which is the previous eon's exponential expansion, maybe that will do for you the job that inflation is supposed to do. So there were various things which seemed to fit together. It was not so much the steady state philosophy. I think I felt sympathetic towards that kind of view, but how much of a driving force it was in formulating CCC, I'm not sure.
And is this supposed to be the cycles of the same universe, or are we talking about different, as it were, universes?
Well, I'm using the term eon to discuss, that's why I'm saying not universe, you see. Some people say it's a previous universe. But you see, it's not a different universe in the sense of it's being separate and different. It's connected because there are effects which come through. I mean, that's the whole story. I know I went a long time lecturing to people thinking that I would never be able to be proved wrong, you see. But then I thought, well, there are signals that could get through. They should be there. And in work I've done with colleagues, we do seem to see such signals. And we're having an awful lot of trouble convincing the cosmological community that these signals are really there. But the evidence is pretty strong now. That there are signals which seem to propagate through from one eon to the next.
My final question, what's the one problem in theoretical physics that still puzzles you the most and one that you would like to understand better?
Well, I think let me say the second most is the trying to get the equations to work to go from one eon to the next. There are some issues that need to be sorted out there. I mean, the general picture is there, and the observations don't depend very much on a detailed theory to tell you how to join one to the next and find equations which do that. But that's not the major problem. The major problem is the collapse of the wave function. we need a theory. And at the moment, we don't even have direct observations. There are several experiments proposed or having been in action for a while to try and test to see whether the gravitational contention about when the collapse happens actually does happen. Spontaneously, do we see that? And a detailed theory of how that comes about, that's the major missing theory in the physics, I think. But it's observationally missing too. We don't see directly this effect in any experiment which is done. I mean, it's all mixed up with decoherence, and then you don't know what's going on. So it's a difficult question.
Roger Penrose, thank you very much.
Thank you.